Hi, this video contains the solutions for a couple of AP free response questions. The first being 2000 and, ooh, that's too many zeros there. 20,000 and, just kidding, 2003, number 1. And the other problem in this video, or the other solution rather, would be 2006, number 2. Alright, so, and this is all part of our Chapter 7 right here. Just put that in the video so we don't forget. Okay, so number 1 from 2003, we have this problem. And I'll tell you what, if you see this problem on the AP test and you know what you're doing, happy days. This is just points, giving away points here. So, let's see what we're doing here. We have a student pulling a box across a rough surface. Box has a mass of 100 kilograms. The position as a function of time of the box is this function here. Notice that it is not linear, and it's not even quadratic, so this definitely is not a situation where we have a constant acceleration or constant force. So no kinematics involved here, although it looks like we could maybe use some calculus. Okay, so part A, determine the speed of the box at time 0. So if I know that the position is 0.5 t cubed plus 2t, then the velocity will be 1.5 t squared plus 2, the derivative of that. And you might notice that they, if you paused for a second when you saw it, they said speed instead of velocity. Notice that this is always a positive quantity. So this is in fact the speed of the box. If it wasn't, if this had the possibility of being negative for t values that were positive, then we could throw absolute value signs around that to get the speed, because this is just one-dimensional. Part B, determine the following as functions of time. What is the kinetic energy of the box? Well, the kinetic energy is equal to 1/2 mv squared. So the kinetic energy is 1/2 times the mass of the box times the velocity, which we have right here, 1.5 t squared plus 2 squared. Okay? Please be careful in this kind of exercise and in general to write the left-hand side of these equations. I don't want to see just this and just this. We want to have these complete. This is like the version, this is the math/science version of writing a complete sentence, right? A complete sentence is the equation with both sides represented there. 2, the net force acting on the box. Well, I know that net force is equal to mass times acceleration. And I have the velocity here, so the acceleration would be 3t. And therefore the net force as a function of time is equal to mass, which is 100, times the acceleration, which is 3t. And in part 3, they would like to know the power being delivered by the box. Well, they kind of set us up for that, didn't they? Power is equal to force times velocity. So power here would be equal to the force, 300t, times the velocity, which is 1.5 t squared plus 2. You can simplify these things or not. The College Board really does not care about that, so don't stress yourself out. Calculate the net work done on the box in the interval from time 0 to time 2. Well, net work is equal to the change in kinetic energy. So the net work done from time 1 to time 2 is equal to 1/2 mv, the velocity at time 2, squared minus 1/2 v at time 0 squared. So that's 1/2 m. The velocity at time 2 is our velocity function. At time 2, 2 squared is 4, and times 1.5 would be 6. All right. Minus 1/2 m. The velocity at time 0 would be 2. We're good there, right? Just looking for mistakes. I don't think I made any there. Squared, sorry. V squared. So I've got, what's this? 50 times 36 minus 4. So 50 times 32. That's about 16. The right number of zeros. I think that's right. 1600 joules. And if I made a mistake in there, it's only for plugging numbers in and being careless. The concept is at least correct. And then in part D, they're awfully fond of, our friends at the College Board, asking us questions like this to see if we can understand what would happen if we tweaked something a little bit that's greater than, less than, equal to. So indicate below whether the work done in the box by the student, that's key, the work done by the student in the interval from 0 to 2 would be greater than, less than, or equal to the answer in part C. So let me draw a quick force diagram of the box. There's the force of gravity, the normal force. Here's the force of the student pulling. And these are not constant, these forces. And I know that because of this weird cubic position function that we got, right? But anyway, I know it's a rough surface, so there is a frictional force. So the net work, well, let's write this first. The net force is equal to the force of the pull minus the force of friction. And then likewise, because forces are the things that do work, the net force is, the net work is equal to the work done by the pull minus the work done by friction. And I think the answer to our question is right there in that equation. The question is, the work done by the student, well, that's this, right? This is the work done by the student. Is that greater than, less than, or equal to the answer in part C? The answer in part C is here. So the work done by the student is equal to the net work plus the work done by friction. Right? I'm just adding that to the other side. Therefore, it is greater. And you can explain this in words if you want to. You can kind of say something like what I just said there. But a force diagram and an equation like this, especially this is the punchline here, is I think that definitely is a good explanation. That would satisfy their requirement for an explanation. It doesn't have to be words, words, words. It can be some equations. I think some words help often, but here I think this is a good explanation. All right, there's that one. And now, look at that. Mr. G thinks he's a good. Ha. I don't know what that means, but that was on the back of my scrap paper. So, I don't know if that's me, Mr. Gallagher. And what a good? That's interesting. Let me think about that. Or not. Let's think about this instead. So, this is 2006, mechanics number 2. Nonlinear spring, a nonlinear spring, a nonlinear spring. What does that mean? It means that spring force, that this does not apply. It means that the work done by a spring, 1/2 k x initial squared minus 1/2 k x final squared. Well, that was the antiderivative of this, right? That was the integral of this. So this does not apply. If you're thinking you're going to use those, you're in big trouble. All right, so it's a non-linear spring. It's compressed various distances x, and the force required to compress it is measured for each of the distance, for each of these distances. The data are shown below in this table. Right? So this is kind of like what you guys did. You did not pay attention to the fact that the spring force would be opposite, right? So notice that there's no negative sign in here. That's very much like what you guys did in the lab. So the magnitude of the force applied by the spring, magnitude, so we don't care about direction, is of the form F equals ax squared. Which quantities should be graphed in order to yield a straight line whose slope could be used to calculate a numerical value for a? Well, if you want to graph something and get this be the slope, and you want the thing to be a straight line, then this has to be your y, and this has to be your, sorry, I should say this should be your vertical, and this should be your horizontal. So I would need that. I've got those, but I would need to graph x squared. You need to, just like they have units here, x squared, the units would be meters squared. You're throwing away points and your chance to get college credit for this class, or at least you're calling that into question, or playing chicken with that, or doing something careless with that if you don't pay attention to details like that. That's easy points, right? Don't give that away. So we have to square these values. I guess that's the answer for part A. This is 2006, number 2. So the answer for part A is we're going to graph force versus position squared. And part B, they want us to fill in the table here for whatever we thought we should do. So let's go ahead and do that. 0.05 squared, 0.0025, 0.01. I'm not even going to do that in the calculator. Sorry, that was embarrassing. Would be 0.01. 0.15 squared would be 0.0225. I'm going to be careful with significant figures. I'm always going to keep between between 2 and 4 rather. 0.2 squared is 0.04, and 0.25 squared is 0.0625. Okay, so we're hoping that this comes out to be linear, if this is true what they told us. Now I need to come up with a scale. There's different ways of thinking about this. I'll show you what I think. I'm going to look at what the highest value is, and I'm going to count how many spaces I have here. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and a bit. So I think if I scale by tens, I'll be good here. 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100 newtons. And this is force measured in newtons. I need to label this axis. That's important. It's worth points. And here on this axis I have x squared measured in meters squared. So let's see. My biggest one is 0.0625. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I've got 12 here and 6 is there. So if I made this 0.06, right, I'm thinking 6 is half of 12, then this would be 0.05, 0.04, 0.03. It takes some practice to be able to do this without getting too stressed out. So there we go. Let's see what we can do now. So I have the first one, I've got a force, I've got my x squared is 0.0025. So this would be 0.005. 0.0025 would be halfway there, and a force of 4. So that's right about there. Then I have 0.01 right on this dotted line, and a force of 17 right about there. Then I have 0.0225, so that'd be right here, halfway. And I got a force of 38. And then I have 0.04, force of 68. And then a I have an x squared of 0.0625. And so 106. So right about there. And I forgot to bring a straight edge, so I'll use the McG whatever paper here and try to draw a line of best fit, which looks pretty dang straight there. Something like that. And there we go. And I think I've done everything they asked for in C. Okay, part D. Using your graph, calculate A. Well, A is the slope of this, right? Now, A is not the thing. When they say use your graph to calculate whatever, and you're finding the slope, it's not always the thing that you're looking for. Sometimes the quantity that shows up here is some other more complicated thing, in which case you have to find the slope and set it equal to whatever is here in place of the slope, right? Oops, sorry, I'm circling something. Whatever's here. Here it's just A, so A is the slope. So let's see. I'm going to pick a couple points from my line of best fit. I'll pick this one, and this one looks pretty good there. So let's see. You'll have to trust me that my points are 0.005, 10, and 0.035, 60. So I'm going to find the slope, which is delta f over delta x squared. That's force would be 60 newtons minus 10 newtons. That's y minus y over x squared would be 0.035 meters squared minus 0.005 meters squared. That's 50 newtons over 0.03 meters squared. So 50 divided by 0.03. So I get about, we'll go with 3 significant figures, 1670. And don't forget the units here. That's probably worth a point. Sorry, let me slide that over. Right, that's probably worth a point. Oops, sorry, messing with my apparatus here. I should not do that while I'm filming. Okay, so there's that. I think in their scoring guide they have 1700. What are the? You might be wondering, what are the acceptable answers here? Like how much of a range of answers would they take? They're fairly lenient here. You can't have something that's wildly different than that. You have to clearly have drawn a decent line of best fit and calculated slope correctly. But if you've done that, then I think you're good, right? So something in the maybe say 1600 to 1800 range, I think would probably be acceptable. But just try to be careful, and you should get something that's fine. All right. Now, let's see. That was part, I wrote B next to that, but that was part D. Now, the spring is then placed horizontally on the floor. One end of the spring is fixed to a wall. So this is like that diagram 7-9 or whatever it was that they kept referring to in homework problems. So we've got the spring mounted on a wall, and a cart of mass 5 kilograms moves on the floor with negligible friction and collides. So I get a cart coming in this way, and it collides head-on with the spring, compressing it a maximum distance of 10 centimeters, right? That's the compression there. I'll call that delta x. So you can imagine that cart comes in, compresses the spring a little bit, right? And we want to calculate the work done by the cart in compressing the spring. So the cart, let's think about whether that's positive or negative. The cart's coming in this way. The work done by the cart on the spring. The cart is moving the spring in that direction, right? So those are the same direction, so that will be positive work. So the work done by the cart on the spring, now the spring is doing work on the cart too, and that would be the opposite direction, so maybe we could recognize this. Right? The work done on the cart by the spring is equal but opposite to the work done on the spring by the cart. Well, that makes sense, right? Newton's third law. It's equal and opposite force. When these two things interact, the forces are equal but opposite. So when we take the area under those forces, they would be equal but opposite. And I know the work done by the spring, so is equal to, well, now let's be careful here because this is not a linear spring, right? It's not a linear spring. We need to find the area under the force function, right? And since we have this negative here, I would need a negative here. This is because I'm finding the work done by the cart. That's what they say. I'm expecting it to be positive, so we'll hope that that's true. So I would need to find the area from, let's say, it's compressed a distance of 10 centimeters. So that would be like from equilibrium length to negative, right, because it's getting compressed that way. And the force function is, well, we found that's the A, right? It's this. And I'll tell you what, there is no reason at all for you to get manual. In other words, do this without your calculator. So I have, unfortunately, for you, because you probably have a new one, I have this. So I'm going to use this negative sign to flip these. Well, actually, no, I won't. I will just do it this way. So negative math 9 gives me my fn int. You might have your nice integral symbol. So I'm doing this function. That goes in first, 1670 x squared, comma x, comma 0, comma negative 0.1, because it's getting compressed. And those two negatives should cancel each other out, and we should get about 0.56. This is work. That's joules. Okay. Remember that we talked about at the beginning of this problem, you can't use this because it's not a linear spring. The reason, or the place, how we got this equation, we got this work done by a spring equation by taking the antiderivative of this, right? Antiderivative of negative kx is negative 1/2 kx squared. That's where this came from. So if the spring is an ax squared spring, that's going to give it a different kind of antiderivative. And you could do this problem here if you want to. You can do 1670 over 3x cubed and plug the numbers in. But calculator is allowed on all parts of the AP physics test, so I'm not going to stress myself out with that. I'm just going to do it with the calculator. That's a skill we're supposed to know. Let's see, we got one more part here. Calculate the speed of the cart just before it strikes the spring. So here, what we've got to recognize is that the speed of the cart is being taken away by the work done on it, right? So the speed of the cart, kinetic energy of the cart, before it hit the spring is equal to the work done by the spring. Right? Or maybe it would be better to say it this way. Maybe it would be better. Let's scratch that. Say the net work done the net work is equal to the change in kinetic energy. Right? Well, what's doing work on the cart? The spring is doing work on the cart, right? That's the only thing doing work on the cart. So the work done by the spring on the cart is equal to the change in kinetic energy, which is equal to, well, the final kinetic energy is 0 of the cart, right? Because it stops and then turns around. And the initial kinetic energy is 1/2 mv initial squared. So here, remember that the work done by the spring is opposite to this. So we have here negative 0.56 joules is equal to negative 1/2 mv initial squared. And then I think we can just solve that pretty easily. The two negative signs cancel out, which is good news. We would pause and scratch our heads and look for a mistake, a sign mistake, if we didn't have those negatives, because they need to cancel each other out. We can't take the square root of a positive number. So there's my energy. I'm going to multiply it by, well, let's see, 1/2 and then another 1/2. So I'm going to multiply by 4 and then take the square root of that. And, oops, that's not the square root. And take the square root of that. That should do it. That's about 1.49 meters per second. And that is how you do physics. So that's if that seemed kind of hard, like kind of parts of those seem kind of hard, that's okay. This is real free response questions, and not to give you an excuse not to try to do as well as you can. That certainly wouldn't be the reason that I would tell you this, but you need to remember, kind of file away in the back of your mind, that the score that you need to get a 5 on this AP test is round about 57 to 60% or so. So on one of these questions, you'll see scoring rubrics for these soon and more often as we go through the year. This entire question would be worth 15 points. So a 9 out of 15 would be, we would consider that to be a decent score, right? That'd be like our cutoff for an A. So please keep that in mind, and we'll see as we have more of these how we do and what those scores mean. All right.